Hi everybody. In this video, I'll be talking about thermodynamics. I'll be talking only about the theory part only, but it will be limited to first and second laws. And I'll do another video on Gibbs free energy and the applications of Gibbs free energy. So before you study thermodynamics, I want to know what it is. In thermodynamics, we study the concepts of heat and temperature and internal conversion of heat or other forms of energy like mechanical energy. So before we move on to the first law, the zeroth law, first law and second law, imagine that you're carrying out an experiment in the lab. So that, let us say, call the system experiment. Everything around it, normally thermodynamics we carry out at 1 atm because outside it's open, okay? But then we apply pressure for different status, but the surroundings. So in the system, things could change, but the surroundings is everything else other than the system. Both together, we call it the universe. Okay, it's the first thing. Now, in a system and a surrounding, as you can see, the system inside the surrounding, there could be exchanges. You could have the exchange of material, or we'll call it mass, and energy, maybe in the form of heat. Okay. So this mass and energy could go out of the system or go from the surroundings to the system. This is so. Let me read here to show that this is the boundary between the system and the surrounding. Okay. So and work too. Okay. So the things that could exchange, flow in and out, would be mass, energy, that's the heat. You can also keep it as heat. Work. Now, if this flow is loved for all three, then we call it is an open system. So it's not, no restrictions. So the entire system is open. So the mass, the material could go out and come inside from the system and from the surroundings. The work could happen and the heat could get exchanged. That's the open system. Now, if you tell a closed system, so this, if this system is closed, only work and energy could be exchanged. So only now it's coming, and only work and energy. Mass flow does not happen. So whenever the mass flow doesn't happen, you got a closed system. The next one is, if this is an isolated system, because in thermodynamics we're studying about these exchanges. So first of all, we have to define within a system whether when we are working on a system, it could be an open system, so there's no control. If it is a closed system, we know there's a control of the material or the mass going in and out, but work and energy goes. But if it's an isolated system, then nothing goes in or nothing goes in. So the work doesn't happen, energy or the heat. And mass. So isolated system means that nothing happens. Okay. Then, so those are the types of system: closed, open, or isolated. Then there are certain thermodynamics processes I want. So these are the definitions. So, because when we do questions, you will know how to apply this knowledge to solve problems. It's just theory and giving you the knowledge that is necessary to solve those problems. So thermodynamics processes can take 4 types. Adiabatic process. So the earlier the relationship between the system and the surroundings, right? Together we call it universe. Now here, the process. Adiabatic process. In an adiabatic process, no heat transferred in or out of the system. So certain processes are controlled in a way, we make it adiabatic. That means we control the transfer of heat in or out of the system, into the system or out of the system. Okay. So when a process is happening, if we can control the heat and no heat goes out or goes in, then we control the heat. Then we know that heat is a constant there. Okay, that is what the adiabatic process. Okay. Then isochoric. Isochoric process. This is where the volume is held constant. Can you remember when we were studying gas laws? We kept one constant and we talked about, like, out of the pressure, volume, and temperature, we kept those constants. Okay, so this is a case like so. Isochoric process, the volume change does not happen. Okay? So if I say isothermal, that you should be able to. If I say isothermal process, we keep the temperature constant, or temperature doesn't change, no change. Okay. Then isobaric pressure process is constant, that means no change in pressure. Okay. So I want to add to this. So these are the definitions you need to know. You may use all of them, or you may not use them, depending on the situation. So, but you need to know. So there are state properties, path properties. Okay. State properties are the properties that do not depend on the path, but they they are fixed. So these state properties define the current state of the system. Okay, so the such things are the temperature. So if you give the temperature of system, you know that okay, here is a system that is at this temperature. It could be defined by this temperature, pressure, volume, internal energy. I'll put U here. Internal. We just answer the delay is because of the my pen is not right. Internal energy. Enthalpy. You know this one, enthalpy. This before you come to thermodynamics, you should have studied enthalpy as a law. So we say H. Entropy. Talk about the second law, entropy, and Gibbs free energy. Energy. You put G here, Gibbs free energy. Okay, so those are the state properties. Okay, we can say state properties, state variables, state functions. So now these temperature, pressure, they do not depend on the path taken to go from one state to the other. So we have from state one the state property. So this is state one, this is state two. Whether it's going to take the path A or path B, the difference between it only depending on the state, not the path. So these are path independent. If you have done Hess's law is dependent on that. So only on the path, but not only on the state, but not on the path. Okay, when you calculated delta H values, that's what you did. It only depends on the state. It doesn't matter how you got from state one to state two. It could be this route, it could be other route, it might go like that, but it doesn't matter because H or enthalpy is a state property or function. So when it comes to path properties, path variables, functions, these would depend on the path taken. So if you're going from one to two, take this way, your straight path or zigzag. 1, 2, 3, these will have different values because they are path dependent. They are the heat and work. Heat and okay. So the next is we will talk about the first zeroth law of thermodynamics. Zero. Now in the zeroth law, what it tells, what it defines is, we'll say you have three systems. See. that are in equilibrium, A is in equilibrium with B when it comes to the heat, all those properties we talked, and B is in equilibrium with C, then by that premise we can say A is also in equilibrium with C. That's what the zeroth law says. Okay. So in the zeroth law, we say if two systems are in equilibrium, we say temperature, right? If there's a temperature equilibrium and temperature equilibrium here, then A and C would have the same equilibrium. Okay. So if two bodies are in equilibrium with a third body independently, like in this case, independently with B, C is in equilibrium with B and A is in equilibrium with A. B is in equilibrium with A, then A and C would also be in equilibrium with each other. That's the zeroth law. Okay. Now, that's all you have to know about it. Okay. So then the first law of thermodynamics. So the first law of thermodynamics which is also known as the law of conservation. What it tells is energy cannot be created or destroyed. So the energy cannot be created or destroyed. What it can only do is change from one form to the other. So this universe changing energy, it's zero change. There's no change. It's always remains the same. Okay, but the energy cannot be created or destroyed, but it can be converted from one form to the other. So it can be converted to work, not completely, but it could. That's what. So the energy is conserved. That's what the first law of thermodynamics tells you. Okay. Now, if we go on to write an equation for that, tell Q as the heat, small q, uppercase Q, doesn't matter. So the law is given as delta Q equals delta U. So the heat change, this is the first one, right? Okay, change heat, maybe it is given, change means either given in or the heat is given into the system or the out. Okay, there are some distinction I want to make because I don't know whether you trying to study thermodynamics in the, so this is in chemistry thermodynamics, but sometimes when you do in physics, there'll be some difference you might notice, but I want you to understand that. So system, that is surroundings. So we're talking about this first part, okay? So you can consider whatever. So we know all the processes, we know the properties, path variables, state variables. Okay, so in this system, we are trying to talk about the work and the heat exchange. Okay, the heat and the work. Therefore, it is not an open system. We are not going to talk about the materials or the mass moving. So we will talk. We'll consider this as a closed system for materials or the mass, but it is open for the heat and the work to go in and out. Okay. So that change is given by delta U, that is the internal energy of the system, and the change. So this is the internal change. That's the work. So that is the formula, but at times they will also write that. Okay. Now, when we are studying chemistry, okay, so the energy that is given into the system. So the reason this, okay, so these two equations we take that there's a positive sign, there's a negative sign sometimes. Okay. Now the work, this is the work. Just if the work is done on the system, we call it positive. Okay. And use this in chemistry. So that's the reason. So always check the definition. If the, or you can write the definition. I use this because of that. So the work done on the system, it's called positive. Then work done by the system towards the outside. So if you have a gas expanding, it is doing the work. It is the work done by the system. Okay. So that's the difference. That is why that sign changes depending on the situation. So in chemistry, the work done on the system is positive. Okay. In physics, work done by the system is positive. So let me go through it again with the so we're talking convex here. But if you see in a physics book, then you might wonder. But if you read it, you can see that what it's telling is. So if the work is done on the system, work done on the system is positive. Yeah. When it comes to physics, work done by the system. By the system on the surroundings. So by the system, the outside is positive. Okay. So now it depends on what we are looking at. In chemistry, we try to study the internal system. Internal. Okay. So anything done onto that system, we call it positive, and we keep it like that to make our calculations easy. Okay. So then in physics, we talk about certain engines. They do things to the outside, right? The engine is doing something to the outside, to the surroundings. So the work done by the system on the surroundings is considered positive. So none of the equations are wrong. It is just what you're looking at. So once you define and put the values, you get that answer correct. Okay? Right. So you know about those ones, and I talked to you about the first law of thermodynamics. So you might sometimes see like EQ because like that. Okay. So you know about the sign conventions. Let me put it again for purposes here in chemistry. So let's go for the ones we know. So if the work is done on the system, that is positive. For an example, if you add pressure and compress something, so we'll say compression. Okay. If a gas is expanding, then negative expansion. Okay. If nothing happens, so if the volume is constant, volume if so if it's an isochoric system, like if the volume is constant, then zero, no sign. So if negative, if the gas is expanding, positive, if the gas is compressed, the volume is constant, because when the gas expands or when you press it, the volume changes as a, but if the volume is kept constant, then the W is zero. Similar to that, the heat also, if we give heat into the system, it is positive. So into the system. So heat is supplied to the system, positive. If the heat is given out from the system, it's negative. If no heat exchange happens, then it's zero. It's more or less adiabatic, right? That's why we learn those terms, okay? Adiabatic. All right. When it's come to the temperature, so in the system, if the temperature increases, I'll put it like that, then it's positive. If the temperature goes down, okay. If temperature remains same, then what it means is constant. Is constant, that is isothermal system. So in an isothermal system, delta U is zero. No change happens. Now these are the things we use when adiabatic system heat is constant. This is isochoric. Right? Do a small example. So if we'll say we were asked to calculate the change in a system, change of internal energy, we are asked to calculate delta U of a system. If we added 5,000 joules of heat, Q, right? And it does 3,000 joules of work. Remember, work is also work. It's expressed the unit for work is joules to K, because work is energy. So work, that's W, right? Now use the our signs. Okay, so our sign convention is delta Q equals delta U plus W rect. So delta U would be delta Q W. So asking is the internal energy. That's 5,000. So when I say why it's delta, it's only one value. So think that at the beginning it was 0. Now we added 5,000. So the difference is just 5,000. That's what it means. Okay. 5,000 minus 3,000. Get 2,000. That's how we follow. This is using the first law. Okay. Yeah. So we studied, we know all the definitions. We know how we use this formula for chemistry. Delta Q equals delta U plus W is that. So addition of internal energy and work together, we get the heat change. Physics is just negative sign, but we are talking about chemistry. That's why I stick with this. Okay. Then when it comes to the path properties and everything, we have studied that part too. Now we are going to talk about the second law of thermodynamics. Okay, we know the zeroth law, we know the first law. So the second law we talk about entropy. Entropy, that's S, we can say disorder. Okay, so anything that happens in nature, which is any natural reaction, okay, we say if it's a hill, a ball rolling down, the natural process is for the ball to roll down. It happens in a way to increase the disorder. All natural processes bring disorder and they are irreversible. Okay, because they can reverse them. But certain instances, we can do certain reactions if you do it very slowly, and we may be able to create a situation where reversible reactions. Okay, we can have a reversible reactions at times. Okay, so there is the definition. So that change of that entropy is the second law includes. Okay, so in the first law, we says that the energy remains constant, conservation of energy. We know that that is a combination of, in chemistry, combination of internal energy plus work. We get that change in the heat. Okay, heat energy. Now, in the first law, we can also find the quantity of energy transfers. We saw, we did the calculations. In the second law of thermodynamics, we say any spontaneous process or any natural process. Okay, so in addition to natural things that happen naturally, spontaneous, they happen in a way to increase the entropy. Okay, so entropy is given as generally more than 0. So the change in the entropy of the universe is always more than 0. It's a positive value. Entropy actually measures the randomness, how things go randomly. So for an example, if you are sitting in a class in an orderly fashion, it adds stress, it's high energy state. And if you're allowed to walk around and talk to each other, then it is lowest energy because there's no strain, and that is the most stable, and it has increased the entropy. Okay, so if you have two systems here, so we'll say you have molecules here, they vibrate, they move about, so there's some entropy here. Okay, and then you add energy to that, and then you get the second system. Because more energy there, these can move faster, and the position of these molecules keep on changing faster. Here it was slowly moving, so therefore S2 would be higher than S1. So the delta S has increased the change. That's what it means. Okay, so the entropy changes when you add heat, and second law of thermodynamics states that natural or spontaneous reactions happen in a way to increase the entropy. Okay, so going along with the entropy change, so in a reversible process, how could you get a reversible? It's difficult, but so we'll say I have a system like this. I have a piston here, so I have molecules. Okay. Then I slowly pull this piston outside. So that's this state one. You can see from here, I have expanded by that, thus giving these molecules more space to move about and have increased the entropy. Right? Then I can, so I move this very slowly. Okay, this is hypothetical situation I'm talking about. When you move, then you change the energy and things. But so first I pulled it upward, and then I can slowly put it back. So that's a reversible, just for you to understand, right? In a reversible process, we can say delta S equals the Q over T. Okay, so that is for a reversible process only. Remember that. So you can have a condition telling that it is reversible, and then apply the equation if it is reversible. So always delta equals delta Q over T for a reversible process. Okay. Now, so entropy, a measurement of disorder, randomness. So we can give it in energy term. This is the energy of disorder. Okay. Increases when heat is added or removed from the system. But because I did it very slowly, I increased the disorder just by giving extra volume, and then I put it back to the same original position and made it reversible. So I have taken it back to the, if we measure the randomness in form of the energy of disorder, then we took it back to that same form by pressing that piston back. Okay. So in general terms, it happens in a way to increase. Okay. So these terms, you know, the heat, this is the heat here. This is the heat transferred to the system. That's the temperature at which it was done. And always temperature should be in Kelvin, that we know when you did gas laws. And delta S is entropy, that's the energy of disorder. Or randomness. Okay. So this was for a reversible. If it is irreversible process, that happens in nature, spontaneous, natural, the things that happens in nature, natural reactions, then the reaction would be delta is going to increase, right? Always. So then Q would be the description. All right. I'm going to stop it there, and in my next video I will talk about the application of this law and then going on to Gibbs free energy.